In this video, I'm going to show you how we can use trigonometric identities to prove other identities. Here you can see a list of basic trigonometric identities that you have to be familiar with. Pythagorean identities, reciprocal identities, and quotient identities. We want to use these identities to prove other identities, like this one here. We want to prove this relation. And as you can see, this is not a basic example. This is a little challenging example. To prove this identity, first, usually we start from this side which is more complicated. By looking at this, we can see that the left side is more complicated than the right side. So it's a good idea to start from this, simplify it, and try to make it like the other side. And if you notice, in the left side we have tangent and cotangent. So it can be a good idea to write tangent and cotangent in terms of sine and cosine. Because when we look at the other side, don't forget, we want to get from this to this expression. In the other side, in the right side, we have only sine and cosine, not tangent and cotangent. So it's a good idea to write tangent and cotangent in terms of sine and cosine. So this is the first thing that we can do here. Maybe you want to start this question in another way. Here you immediately notice that you have two fractions. So maybe you think to doing a common denominator between these two fractions, and then you want to write tangent and cotangent in terms of sine and cosine. You can do it that way also, but maybe it's better to first write tangent and cotangent in terms of sine and cosine. So let us start. So I am going to write this in the form of cosine theta all over 1 minus sine theta over cosine theta plus sine theta over 1 minus cosine theta over sine theta. Now we have to simplify these fractions. To simplify these fractions, you can do it in different ways. Maybe you are thinking to doing a common denominator between these two, doing a common denominator, then dividing the numerator by this. That is one way for simplifying these fractions. But the better way is to try to get rid of the denominators first. How we can get rid of these denominators without doing any common denominator? Let me tell you how we can simplify these fractions in a better way than doing a common denominator. When we look at this, we notice that we want to eliminate this cosine. How we can eliminate that? Simply, we can multiply the numerator and the denominator. And also for this, we want to get rid of this sign here. To do that, we can multiply the numerator and denominator at the same time by a proper expression to help us eliminate the denominators. For the first fraction, we want to get rid of this cosine. What expression we have to multiply the numerator and denominator by that? Cosine, of course, because we want to get rid of cosine. So we multiply the numerator by cosine theta, and we multiply the denominator by cosine theta. What happens by this? In numerator we have cosine times cosine, which is cosine to the 2 theta. If we multiply cosine by 1, then we have cosine theta minus. When we multiply cosine by this fraction, cosine from denominator with cosine from numerator cancels, and we have only minus sine theta. So the denominator is cosine minus sine. For the next fraction, what we have to multiply the numerator and denominator? Of course, we have to multiply by sine. So we multiply the numerator by a sine theta, and we multiply the denominator also by a sine theta. Then the numerator would be sine to the 2, and the denominator is sine theta times 1, which is sine theta. Sine theta times by this would be a negative cosine theta. These two denominators seems to be similar, but are they exactly the same? They are, if you attention, they are negative of each other. Let me tell you the reason. Attention to these two expressions, a minus b, b minus a. Are they equal? No. But if you attention, these are negative of each other. A minus b is negative of b minus a, which means that if we multiply this by a negative, it would be that expression. Negative of b minus a is exactly a minus b. Let me tell you the reason. If we multiply negative by b, then we have negative b. Negative times negative is plus a. A minus b is exactly this. And you can check this by numbers also. For example, suppose we have 5 minus 2 and 2 minus 5. This equals 3, this equals negative 3. What is the relation? They are negative of each other. So, actually, these denominators are the same, but negative of each other. Not the same exactly, negative of each other. So, if we want, we can erase this denominator and we can replace it with this. But because we want to replace this with this denominator, we have to put a negative here, because this is negative of that. So, let me erase this denominator and replace it with cosine minus sine. Then I can put that extra negative here. Let me remind you, what was here? Sine minus cosine. If we factor a negative from this, expression, it would be cosine minus sine. So we replace it with cosine minus sine and we put this negative here. This is what happened here. Now that the denominators are the same, we write one of the denominators and we subtract the numerators. Cosine to the 2 minus sine to the 2. When we look at this, we remember a famous identity. A to the 2 minus b to the 2 can be written as a minus b times a plus b. By using this identity, we can write the numerator in the form of cosine minus sine times cosine plus sine. And then the first bracket in numerator cancels with the denominator. What remains from this? From this exactly we have this. So this equals the other side. So we prove that. So finally this equals to cosine plus sine. And this finishes the proving of this identity. So we started from left side. We simplified that and we got to this expression. So we get to the other side. So this completes the proof of this identity. You can try the other way, which is doing a common denominator between these two first, then writing the tangent and cotangent in terms of sine and cosine. You should be able to finish and prove this identity in that method as well. But I preferred to rewrite the tangent and cotangent first in terms of sine and cosine. Then I did the common denominator and I got to the other side. Now look at this challenging example. 1 plus cosine plus sine over 1 plus cosine alpha minus sine alpha equals secant alpha plus tangent alpha. To prove this identity, which side is more complicated? Probably this side should be clear that is more complicated than the right side. So it can be a good idea to start from this, simplify it and get to the other side. And the reason that we think that the left side is more complicated because we have this big fraction with 3 terms in numerator, 3 terms in denominator. But how we can simplify this expression? How we can simplify 1 plus cosine alpha plus sine alpha all over 1 plus cosine alpha minus sine alpha. If you have watched my other video for proving trigonometric identities, which covers more basic examples, probably you remember one of the techniques for proving identities is multiplying by the conjugate. Here we can multiply the numerator and denominator by the conjugate of this, and for that suppose this as the first term and this as the second term, and so the conjugate of the denominator is 1 plus cosine alpha plus sine alpha. So we multiply the numerator and denominator by this expression, which is the conjugate of denominator. By doing this, what is the denominator first? Attention, this is like a minus b times a plus b. And we know that the answer is a to the 2 minus b to the 2. So the answer is 1 plus cosine alpha to the 2 minus sine alpha to the 2, or sine to the 2 alpha. This is for the denominator. But what about the numerator? And for multiplying numerator by numerator, you can multiply term by term. The first term in the first term, the first term in the second term, the first term in the third term, then move to the next term, and so on. Then you would have 9 terms in the answer. And then the numerator has 9 different terms, which is a lot. Is there a better way, more efficient way to multiply numerator by numerator? If you pay attention, these two are the same. The better way that you can multiply the numerator is to suppose this as a and this as b. Again, this is a and this is b. So we have a plus b in the first numerator times by another a plus b in the second numerator. And we know that a plus b times a plus b is a to the 2, 2ab, b to the 2. Because a times a is a to the 2, but then we have a, b, b, a, and this is a famous identity. And b times b is b to the 2. So this way is much better than multiplying the numerator by numerator, term by terms. So let's do it this way. If we multiply the numerator by numerator, we have a to the 2. What is a? A is 1 plus cosine. So numerator would be 1 plus cosine alpha to the 2. Then we have 2ab, 2 times 1 plus cosine alpha times y sine alpha. And finally we have b to the 2, which is sine to the 2. This is the numerator. Now let's simplify the numerator and the denominator. For the denominator, if we expand this, 1 plus cosine to the 2 is 1 to the 2, which is 1, plus 2 cosine alpha plus cosine to the 2 alpha, minus sine to the 2 alpha, sine to the 2 alpha. This is the denominator. And attention, for expanding this to this, again we use this identity. A plus b to the 2 is a to b to ab. We use that identity to expand this. This is for the denominator. But let's back to the numerator. In the numerator, if we open this, we have 1 to the 2, which is 1, plus 2 cosine alpha, plus cosine to the 2 alpha. And let's leave this in the factored form. I have a good reason for that, to leave it in the factored form. The reason that I'm not going to multiply this in this bracket, because by multiplying this sign in this bracket, nothing would be simplified. But the reason that I expanded this one is that when I have this term here, the terms inside this expression and this term here would combine by each other and we can simplify them. So at the end we have sine to the 2 alpha. Now look at this. Cosine to the 2 and sine to the 2, based on the Pythagorean identity, sine to the 2 plus cosine to the 2 is 1. So the sum of these two terms is 1. 1 plus this one here would be 2. So in numerator we have 2 plus 2 cosine alpha plus, so don't forget, the sum of these two is 1. 1 plus this one is 2. So these are gone and we have 2. And we have this term and of course this term. So plus 2 bracket 1 plus cosine alpha times by sine alpha all over. Now look at the denominator. In the denominator, this term is in terms of cosine. This term is also in terms of cosine. But we have 1 minus sine to the 2. But we remember that 1 minus sine to the 2 is cosine to the 2. Let me remind you the Pythagorean identity. Sine to the 2 plus cosine to the 2 is 1. If you move this term to the other side, then cosine to the 2 would be 1 minus sine to the 2. So whenever we have 1 minus sine to the 2, we can replace it with cosine to the 2. Here we use this identity. So 1 minus sine to the 2 is cosine to the 2. Plus this cosine to the 2 would be 2 cosine to the 2. So in total we have this in the denominator, 2 cosine alpha plus 2 cosine to the 2 alpha. The 2 cosine is here. We have 1 cosine to the 2 here, and these 2 also is a cosine to the 2. In total we have 2 cosine to the 2. Look at the numerator. All the terms in numerator have a 2 as a common factor. So we can simplify those 2's in the numerator with the 2's in the denominator. But let's keep it in this way for now. Later we simplify the 2 from numerator with the 2 from denominator. Look at these 2. What do you notice? You can factor a 2 from those 2 terms. If we factor 2, then we have 1 plus cosine alpha. And then we have 2 times 1 plus cosine alpha times by sine alpha in the numerator. So in numerator we did basically nothing, just we factored a 2 from the first 2 terms. And in the denominator we factor a 2 also. We can factor basically a 2 cosine. The cosine is common between these 2 terms. If we factor 2 cosine, then we have 1 plus cosine alpha. So from these 2 terms we factor a 2 cosine alpha, and then we have this. Now look at the numerator. What do you see in the numerator? You can see that this is common between this term and this term. In numerator we have this big term and this big term, and 2 times 1 plus cosine is common between them. So we can factor 2 times 1 plus cosine alpha from this term and this term. By factoring this, what remains from the first term? If we factor that from the first term, everything from the first term is gone, and so we have to write a 1 here. 1 times by this would be exactly this. What remains from the second term? From the second term we have a sine alpha, so plus sine alpha. And in the denominator we have 2 cosine alpha times 1 plus cosine alpha. Finally, it seems that we are going to finish this question. 2 with 2 cancels, 1 plus cosine with 1 plus cosine cancels, and we have 1 plus sine alpha over cosine alpha. Now separate numerator over denominator. This equals to 1 over cosine plus sine over cosine. What is 1 over cosine? 1 over cosine based on reciprocal identities is secant alpha. Sine over cosine is tangent alpha. The other side. This finishes this example here. We proved this complicated identity. Now look at this example. We want to prove that tangent alpha plus tangent beta times by 1 minus cotangent cotangent plus cotangent alpha plus cotangent beta times by 1 minus tangent alpha tangent beta is equal to 0. So, how we can prove this? One way can be to write tangent and cotangent in terms of sine and cosine. The other thing that you can keep in your head is that cotangent and tangent are reciprocal of each other. You know this. Cotangent is 1 over tangent. So tangent, if we multiply this by this, if we do a cross multiplication, tangent alpha times by cotangent alpha is always 1. Which makes sense because these are reciprocal of each other. When you multiply an expression by its reciprocal, the product is 1. And if you pay attention, in this bracket we have tangent, in the other bracket we have cotangent. So maybe it's not a bad idea to multiply the brackets by each other, and probably many terms cancel each other. So let's see what happens if we multiply the brackets by each other. And again, I have to mention, the other way to simplify and get the answer to prove that this expression is equal to 0 is to write tangent and cotangent in terms of sine and cosine. You can try that way as well. There is no unique way to prove trigonometric identities. There are different ways usually for proving these type of identities. Let's see what happens if we multiply the brackets by each other. Tangent alpha times 1, we multiply the first term in the first term. Attention, we are doing a FOIL. We are using basically a FOIL method. We multiply term by term. Tangent alpha times 1 is tangent alpha. Then tangent alpha times by negative cotangent alpha, cotangent beta, we have negative tangent alpha. Tangent alpha, cotangent alpha, cotangent beta. Attention, this is 1. So only we have cotangent, this is cotangent. So let me write this a better way. So tangent alpha, cotangent beta, this is. Then let's multiply the tangent by 1. So we have tangent beta. Then we have minus cotangent alpha, cotangent beta, tangent beta. You can put this tangent here because it's multiplication. It's really not important where to put this tangent. You can put right here in the middle at the end. It's multiplication. The order doesn't matter. Now let's multiply the other bracket. Cotangent alpha times 1 is cotangent alpha. Then we have cotangent alpha times by this, so we have minus cotangent alpha, tangent alpha, tangent beta. Now multiply the cotangent beta in the bracket. By multiplying the cotangent beta in the bracket, we have cotangent beta minus cotangent beta, tangent alpha, tangent beta. Now let's see what we have here. We have tangent alpha minus cotangent beta. These two, when we multiply these two by each other, it's 1 because they are reciprocal of each other. And we have only cotangent beta. Then we have tangent beta what we have here, the product of these two is 1 because these are reciprocal of each other. Tangent beta times cotangent beta is 1. So we have only negative cotangent alpha. So we have negative cotangent alpha. Then we have cotangent alpha here. Please pay attention. The product of these two is 1. So we have minus tangent beta. Minus tangent beta. And then we have cotangent beta. This term. And for this term, tangent beta times cotangent beta is 1. So we can suppose this term is here. So when we multiply this by this, these are reciprocal, they cancel each other. So we have only negative tangent alpha minus tangent alpha. This term cancels with this term. Minus cotangent beta with cotangent beta cancels. Tangent beta with minus tangent beta cancels. And finally, cotangent alpha with cotangent alpha cancels. Nothing remains. So this equals 0. At first, this example seems challenging. But it's just multiply the brackets by each other. The terms cancel each other. And you get the answer. We prove that this expression is 0. Now look at this example. Sine to the 3x plus cosine 3x all over sine x plus cosine x is 1 minus sine x cosine x. It should be clear that we have to start from the left side because it's more complicated. We always start, not always, but usually we start from the more complicated part. We try to simplify to get to the other side. It happens that sometimes we simplify the left side, we simplify the right side, and we try to get to the same expression. Then this shows that these two are equal. So not always we have to simplify only one side. Sometimes it happens that we have to simplify both sides to get to the same expression. Then it shows that the two original expressions are also equal. But here it seems that only we have to simplify the left side. But we have sine to the 3 and cosine to the 3 with a plus between them. For me, this reminds me this famous identity, a to the 3 plus b to the 3 is a plus b times a2 minus ab plus b2. If you want to be able to do examples complicated like this one, you have to be familiar with advanced formulas, advanced identities in algebra like this. You should be completely familiar with this type of identities, and you have to keep them in your head, not in the formula sheet, because you need them right away. You don't have to look at your formula sheet, try to find an identity to use it to work for the example. No, that way doesn't work. You have to keep the identities in your head so you can use them when you need them. A to the 3, b to the 3. I can see, when I have this in my head, I can see this in this expression. A to the 3, b to the 3. So I'm going to use this for the numerator. By using this, numerator can be written as sine x plus cosine x. Attention, the a is sine, the b is cosine, a to the 3, b to the 3. So it's a plus b, sine plus cosine. The numerator can be factored in the form of sine x plus cosine x, sine to the 2 minus ab, sine times cosine. And finally b to the 2, cosine to the 2, all over sine x plus cosine x. This completely cancels with this. What remains? From this we have sine to the 2 plus cosine to the 2 minus this. But we know that sine to the 2 plus cosine to the 2, based on the Pythagorean identities, sine to the 2 plus cosine to the 2 is 1. So the numerator is 1 minus this. So the numerator is 1 minus sine x cosine x. So we simplify the left side. Then we got to this. This goes with this. And this remains. But this is exactly 1, because the sum of these two is 1, minus sine cosine. And look at this. This is exactly the other side. So we got to the other side. So the only thing that you need for this question is to be familiar with this identity from algebra. A to the 3 plus b to the 3 is a plus b, a2 minus ab plus b2. And remember that when it's negative here, then here is negative, here is plus. This is the identity when between a3 and b3 we have a minus. When we have a to the 3 minus b to the 3, it equals a minus b times a2 plus ab plus b to the 2. Now look at this example. Tangent theta plus cotangent theta to the power of 4 is secant to the 4 theta times cosecant to the 4 theta. Here we have a bracket raised to the power of 4. If you want to raise this bracket to the power of 4, you have to multiply this bracket by itself 4 times. Or you have to be familiar with the identity a plus b to the 4, which is very complicated. So it's not a good idea to even think to this, to multiply this bracket by itself 4 times. The other thing that you can do here is to think to the identities that we have for tangent and cotangent. For tangent, we can write it as sine over cosine. Cotangent, cosine over sine. And then you have fractions here. And you can combine those two fractions. You can do a common denominator and combine these two as a single term. Then when you have a single term to the power of 4, raising it to the 4 would be probably easier. When you have two separate terms with a plus between them, it's hard to raise to the 4. But if you can combine these two to a single term, probably it would be easier to raise it to the 4. So let's try this to see what happens. Tangent is sine over cosine. So we start again from the left side and we try to get to the other side. Cotangent is cosine, not x, it should be theta, sine theta, cosine theta. Sine theta plus cosine theta over sine theta to the 4. To add these two, we have to do a common denominator. The common denominator is cosine times sine. It should be clear for you doing a simple common denominator. We multiply this by sine, so we multiply the numerator by sine, sine to the 2 we have. Here we have a sine, but now it's sine times cosine, so we have to multiply its numerator by cosine. Cosine times cosine would be cosine to the 2. So here simply we did a common denominator between the two fractions. Look at the numerator. In the numerator we have sine to the 2 plus cosine to the 2, but we know that sine to the 2 plus cosine to the 2 by the Pythagorean identity is 1. So we have 1 over cosine theta times by sine theta to the 4. Now, here at this step, we are so close to the other side because now we have one expression without any plus minus here to the 4. And attention, 1 over cosine times sine is basically, first of all, this power 4 is all for all of this. So this is 1 to the 4, cosine to the 4, sine to the 4. But before raising them to the power of 4, attention that this expression is basically 1 over cosine times by 1 over sine. Because when we multiply numerator by numerator is 1, denominator by denominator is this. So we can write this fraction in the form of 1 over cosine times 1 over sine. It is like this. Suppose you have 1 over 6. You can write it as 1 over 2 times 1 over 3. This is a simple algebra rule. to the power of 4. But maybe you wonder why I am doing this. Because 1 over cosine is secant. 1 over sine is cosecant to the 4. So then we have secant to the 4 theta, cosecant to the 4 theta. And this is the other side. So we prove this identity. Please pay attention that here you can raise this bracket first to the 4. Then you have 1 over cosine to the 4 times by sine to the 4. 1 over cosine to the 4 is secant to the 4. 1 over sine to the 4 is cosecant to the 4. This is the other way that we can get to the other side as well. Now look at this example. We want to prove that sine alpha minus tangent alpha times by cosine alpha minus cotangent alpha is equal to the other side. Both sides of this expression, both sides of this identity basically are a little complicated. But which side is more complicated? Probably you are thinking the left side. So, because the left side is more complicated, you can start from the left side. But you know that when you want to simplify the left side, you want to get to the other side. Take a look at the other side. Take a look at the right side. In the right side, we have cosine and sine. These are the trig identities that we have in the right side. But in the left side, we have tangent and cotangent. So it can be a good idea to write tangent as sine over cosine and cotangent as cosine over sine. Because finally, we want to get to the other side. And in the right side, only we have sine and cosine, not cotangent, not tangent. So, of course, we have to multiply the brackets probably by each other, but we have to write tangent and cotangent as sine over cosine and cosine over sine first. So let's do it here. So we start from the left side, but before multiplying the brackets, it's a good idea to write tangent as sine over cosine and cotangent as cosine over sine. Now here you can think to multiplying the brackets by each other. So let's see what happens if we multiply the brackets by each other. Probably there is other way to prove this, but one way is to multiply the brackets by each other and try to get to the other side. If we multiply the brackets by each other, sine times by cosine is sine alpha cosine alpha. Then we have minus this by this. Attention, when we multiply this by this, the sine from numerator with sine from denominator cancels and we have only negative cosine alpha. So minus cosine alpha. Then we have to multiply this by this. The cosine with cosine cancels and we have minus sine alpha. So minus sine alpha. And finally, when we multiply this by this completely cancels with this and we have plus 1. Because minus times minus is 1. Attention, this goes with this cancels with this, minus times minus would be plus 1. Now, if you attention, this expression is exactly this. If you factor this, if you try to factor this, the factored form of this expression is exactly the other side. So we are done. So here we can write this as sine alpha minus 1 times cosine alpha minus 1. Sine alpha times cosine alpha would be this term. Sine alpha times negative 1 would be this term. Cosine alpha times negative 1 would be this term. And negative 1 times negative 1 would be 1. So the only thing that here we did was to write the tangent and cotangent in terms of sine and cosine, multiply the brackets, factor it again because the other side is factored form, and that's it. This is the proof of this identity. I hope watching this video was helpful for you to learn how to prove trigonometric identities with the aim of basic trigonometric identities and other algebra techniques. If this video was helpful for you, please subscribe in my channel and see you in the next videos.